Let's prove one more theorem. This one says that a set is open if and only if its complement is closed. Okay, so we know what an open set is, but we don't know what is complement, and we don't know what closed means. So let's look into those definitions. Okay, so let's start with closed. So we say that a point E is closed. Okay, if every limit point of E, every limit point of E is a point of E. Okay, this sounds a little silly. Let's write it like this. There we go. E is closed if every limit point of E is a point that belongs to E. And then the complement. So the complement of E that we write EC is the set of all points in X, okay, such that P does not belong to E. Okay, so when we are looking, if we have a set E, the complement are all the points that are outside. Okay, we have X here, so the complement would be the shaded region here that is showing all the points that are not in E, points from X. So how do we prove this? So we need to prove both implications, first from right to left, then from left to right, okay? Or the other way around. We are going to do this way. So I'm going to show that if the complement of a set is closed, then the set is open. Okay, and then the second implication is that if the set is open, then the complement is closed. Okay, so let's get to it. When I say that EC is closed, that means that it contains all the limit points. Okay, so for example, let's say this is my assumption. Okay, let me make that very clear that EC is closed, and I want to show that E is open. So to show that E is open, I need to show that for every X in E, there exists a neighborhood, okay, a neighborhood of X that is completely contained in E. Okay, so that is what I need to show, that there exists a neighborhood. Okay, for that, the only thing I know is that EC is closed. So let's say this is my set E, and we have my EC outside, okay? And let's take a point X that belongs to E. So let X belong to E, okay? And because it belongs to E, this is a bit obvious, but then that means that X does not belong to the complement, okay? That's the definition. But because the complement is closed, that means it contains all the limit points. That means that X is not a limit point EC. Okay. So if X is not a limit point of EC, that means that there exists a neighborhood N, okay, of X, such that there is an empty intersection, okay, the intersection between n and the complement of e is empty. Okay, what do we mean by this? So we mean if the intersection between n and the complement of e is empty, that means that n is contained in e. Okay, so we have found a neighborhood of x that is completely contained in e, and that means that e is open. Again, remember we were working with any point x of e. We chose a point x of e, and then using the property that EC is closed, we have been able to show there is a neighborhood around x that is completely contained in E. Okay, that's the definition of E is open. So that finishes the first part. Now for the second part, E is open, then EC is closed. So let's, again, what we want to show is that EC is closed. So we are going to pick X, a limit point of EC, and then we want to show that X belongs to EC. Okay. For that, the only thing we can use is that E is open somehow. Okay, so we know that every neighborhood of X contains points, contains some point from EC, from the complement, okay? So that means that X is not an interior point of E, okay? But because if it's not an interior point, because E is open, okay, that means all the points are interior, so that means that X does not belong to E, or that X belongs to the complement, okay? And because X, we chose it as a limit point of EC, and we have shown that X belongs to EC, okay, that means that EC is closed, and we are done. This finishes the proof.